Okay, so we're going to look at the 4 problems that we saw in class today. Obviously you saw one in a lot of detail because your group worked on that, and then the other 3 you may or may not have really looked at really closely. So this is a chance for you to understand how to do the 3 that you weren't assigned today. This first one is a typical track problem, and you can read the problem, but the track is made up of a rectangular football field, and then there's semicircles on either end. So typically in a track problem, we are given some information about the distance around the track or the perimeter of the entire thing, so rectangle plus semicircles. And we're being asked to find, to maximize the area of just the rectangular football field, right? So when we maximize the area, we're not considering the circular part, but the circular part comes into play with the perimeter. So the first part of the problem says labeling the dimensions x and y. It doesn't really matter which we label what, but I like to label horizontal x and vertical y. Find an equation for the perimeter of the track. Okay, again, if we read up in the problem, it tells us that the perimeter of the track is 1,500 meters. Okay, but the track, keep in mind, is made up of these 2 lengths of x, and then it's made up of these semicircles. Okay, and I remind you here that the circumference of a circle is pi times the diameter. And we have 2 semicircles here, so they're going to make up just 1 full circle. So the perimeter of the track, which is 1,500, is going to equal those 2 x's from the rectangle plus pi y, because y is the diameter of our circle. Again, this pi y, you can really think of it as half of the half of the circumference of a circle plus the other half of the circumference of a circle. So together, these 2 semicircles make 1 full circle. Right, so now an equation for the area of the rectangular football field as a function of x. Okay, so as a function of x means x is the only variable in the formula part of it. Okay, so we can think of area of the rectangular football field is x times y. Okay, and that's great, but this is not a function of x because we have a y here. So we need to find a way to replace y with something that has to do with x. So we're going to go back up here to our perimeter equation and solve it for y. Okay, so if I rearrange, I get 1,500 minus 2x equals pi y. And then I have to divide everything by pi. So I'm going to divide both sides by pi. And now I have something that I could substitute in for y here. So in terms of x, my area is x times 1,500 minus 2x all over pi. Okay, if you by chance called your x and y, you alternated your x or you exchanged your x and y, so x was this vertical distance, the vertical height of the rectangle, and y was the horizontal length, then you're going to get a slightly different equation for area, but it should still work. Okay, at this point, we can just use our calculator to graph this within a reasonable domain. And that reasonable domain is, I don't know, roughly 0 to 0 to 750, 800 or so. I'm just going to do a quick sketch. You can do a better job of it when you do it. Really, it says including all important points. So really, I should label whatever this axis is, the intercept is, and then we have the origin. But really, the most important point, because we're going to be asked down here, what is the maximum area of the football field, is that maximum there. And that maximum, using the calculator, is, looks like 375, comma, 89,525, roughly, if I round it to the nearest whole number. Okay, so you needed a pretty big window to be able to see that 89,000. The maximum area of the football field, 89,525, I don't remember what units I used, meters squared. Okay, so meters squared. And then what dimensions maximize the area of the field? So in other words, what dimensions of the rectangle? The x that your calculator gives you, that 375, is the same as the x on our rectangle. But keep in mind that the y on our calculator is the maximum area. That's different than the y that's in our problem. Okay, so in order to find the y, the y dimension, the easiest way to do it would be to divide the area by the x dimension. So 89,525 divided by 375 looks like it's roughly 239. So x by y is 375 by 239. And again, that's roughly, it's not perfect, but it's pretty close. Now we have the window problem, and I'm only going to look at parts A, B, and C here. The bonus section gets a little ugly, and you're not responsible for that. So I'm just going to look at the first part of the window problem. So Ellie has a window in her house. It's made up of a square with a semicircle on top of it, as shown in the figure. The total area of the window is 525 square inches. So this uses similar concepts to the track problem because, again, we have like a square before we had a rectangle, but a square with a semicircle on it. The difference is that we're being given the area of the window in this case, so the total area of the window, square plus semicircle, is 525, and somehow we're going to use that to answer the questions that follow. So write an equation that expresses the area of the window. Now keeping in mind that the area of a square, the area of a square is just the square of the side squared, right? So that would be x squared. The area of a semicircle, okay, if a full circle is area pi r squared, the area of the semicircle is going to be pi r squared over 2. But in this case, r is actually x over 2. So it gets a little ugly with some of the calculators, some of the algebra when we simplify, but it's overall conceptually not very difficult. Okay, so the total area of the window is 525. So we have 525 is going to equal x squared for the square plus pi r squared over 2. So I'm going to write it all out for right now. Pi r is half of x, so half of x squared, and that all goes over 2. Okay, now we're just going to work on simplifying this so it's not quite as ugly as it looks right now. Okay, 1/2 x squared is actually 1/4 x squared, right? So pi, if I square half of x, I'm going to apply that square to both the half and the x. So I'm going to get pi times 1/4 x squared. If I simplify that, I can write that as pi x over 4. But that is all over 2. Okay, so bear with me. This is actually pi x over 8, right? Because this over here is like saying what is half of pi x over 4. So half of that is pi x over 8. So if I wanted to rewrite this area equation, I'll just write it down here. 525 equals x squared plus pi x squared. Sorry, I forgot the squared over here. Pi x squared over 8. All right, so here's our area equation. And this question is asking us for the side length of the square. So we need to solve for x, which we can do algebraically if we want to. It gets a little bit ugly because we've got that pi in there. You could also just plug this in your calculator. Plug both sides of the equation in your calculator and find the intersection of the line y equals 525 with the function y equals x squared plus pi x squared over 8. So once I do that and plugging in my calculator, I get that the intersection point is at x equals 19.4. So the side length of the square is 19.4 inches. So then it asks for the perimeter of the window. Okay, well, if I look at my window over here, I have an X, an X, and an X. So I have 3 X's. Okay, so that means I'm going to have 3 times 19.4. And then I also have half of a semicircle, so half of the circumference of a circle. If the circumference of a circle that we remember from before is pi d, then half the circumference of the circle is going to be half of pi d, right? And in this case, d is x, right? It's the same thing as x. So we're going to add to our perimeter half of pi times x, 19.4. And if I stick that in my calculator, it looks like I get about 88.7, and that is inches for perimeter. Okay, here we have the open box problem, which you probably did many of these last year. So, I mean, you can go right to writing the equation for the volume of the box if you're comfortable with this, but I added a little question just asking for expressions for the length, width, and height just to kind of remind you how to go about this. So it doesn't matter whether you think of the length or the width as the horizontal or vertical dimension that you see here. But again, just a reminder, this is an open box, or this is a box that's kind of, it's all flattened out, but we're going to fold up these sides here. Right, we're going to fold up these sides, and those sides have a width of x. But that x, if you think in 3 dimensions, becomes the height of your box. Right, so our height will be x. And then our length is, the length of the overall box is going to be like this dimension here. So it's this 15, but minus the x's on either side. So our length we can call 15 minus 2x, and likewise our width is going to be 10 minus 2x. Well, that looks like a 16, but it's supposed to be 10. 10 minus 2x. Use your dimensions to write an equation for the volume of the box. So v of x, or v, equals x times 15 minus 2x times 10 minus 2x. Okay, explain, find v of 3 and explain what the number represents. So v of 3 is 3 times 9 times 4. Right, so what's that? 36 times 3 is 108. So that means that if those corners that were cut out were 3 by 3 squares, right? So if these corners here measured 3 by 3, right, 3 by 3 squares, then the volume of the box would be 108. All right, so what is a reasonable domain for this problem? And then use your calculator to graph the function. Well, if we take a look just by logic, our reasonable domain is anything that's going to make this still be a box, right? So if you think about this, if I make x too big, eventually there's going to be nothing, there's going to be no side of the box. So we're going to look at the most restrictive side. The 10 inches is the most restrictive of the two sides, right? So this x, if you think logically about it, can't be more than 5. It can't even really be 5, because if I take 5 away from both sides, then I've got nothing left of the box, right? I don't actually have a box. So it can be anything up to, but not including 5, right? So we have a domain of like 0 to 5 for our domain. So we can graph that. We can use our calculator to graph this function within that domain. All right, so if I go ahead and again, I'm just going to do this very roughly. You could do a better job of it. If I plot this function, it looks something like this. And it does come back up, but I don't really care about the part that comes back up because I'm only really looking at it under my domain, right? And then use your calculator to find what values of x give a volume of 126 cubic inches. So I'm going to use my calculator to actually graph the line y equals 126, and it's going to end up cutting across my graph like something like that. All right, and at these 2 points, the volume, at these 2 x values, the volume will equal 126, and it looks like it's the x value 1.5, and then about it was like 2.45 or 2.5 or something like that, something close to that. And then I think the final question is probably to find the maximum. What value of x will maximize the volume? So what value of x will maximize the volume? We'll just use our maximum function here. And we find that this point up here happens at 1.96, comma 132. I don't ask you for the maximum volume, I just asked you for what value of x. So the value of x is 1.96. If I asked you for the maximum volume would be 132 cubic, I think it was inches, was the original unit. Okay, and the last problem today made you think a little bit back to geometry, probably, where we're taking this rectangle here, and we're actually going to rotate it around this axis. My pen's not working here. Okay, so we're going to actually rotate it around this axis here. And when we rotate it, what happens is we actually form a cylinder. Okay, and the cylinder has the same height as the rectangle, so y is the height of the cylinder, and then the radius of the cylinder is the same as that width of my rectangle, or x. Okay, so those are going to be the important pieces to this. So the problem tells us that we have a rectangle of a perimeter 12 inches, and a cylinder is formed by revolving the rectangle. Okay, so write an equation for the perimeter of the rectangle. Well, we know it's 12, and our rectangle is just a typical rectangle. It's got 2 lengths and 2 widths, so 2x plus 2y is going to equal 12. Then it says write a formula for the volume of the cylinder in terms of x. So that means we're going to eventually need to have everything with x's, right? So if our volume is pi r squared h, well, keep in mind we said that our r in this case is actually x, and our h is actually y. So our volume is actually pi x squared x squared y, right? But we want it all in terms of x, so that means we're going to have to do some kind of substitution for y. And if we look back at our perimeter equation, we could easily substitute, right? So 6 equals x plus y, so y is equal to 6 minus x. So I could take this and substitute this in here. So my volume equation instead becomes pi x squared times 6 minus x. All right, so now we're asked for a reasonable domain. And again, just kind of using your intuition, if you look at the volume equation, okay, it doesn't make sense for our x value to get anything, to be anything above 6, right? Because if I'm above 6, then I end up with a negative dimension on x, and that just doesn't make sense. Okay, so our reasonable domain is going to be anything from 0 to 6. And then we could grab our calculators and graph that function within that over that reasonable domain. Okay, and when I do that, I end up with something that looks roughly like this. So this is going to cross at 6. Again, this goes up over here, but I don't really care about what happens to the left of the y-axis because I'm only considering the domain 0 to 6. And then I think the next question is, what is the maximum volume of the cylinder? Right, so we could use our calculators to find this maximum point here, and the maximum is at 100.53. Okay, so our maximum volume is 100.53, whatever the units are. I don't think I gave you units this time. So units cubed. And what dimensions of the rectangle? will result in a cylinder of maximum volume? Well, the x dimension is given to us by our graphing calculator is 4, right? And if x is 4, we can go back up here and plug it in. If x is 4, then y must be 2. And that's it.